All right, so introduction to GPS, which you correctly identified as the global positioning system, refers to really a system. When we think about systems, they have different parts. The GPS system essentially has three parts. So next question, and you're welcome to unmute and answer, or you're welcome to answer via the chat box, which is now, what are the three parts of the GPS system? Any guesses are welcome. So what are the three parts? I'll give you a hint. I'm depicting the three parts on the screen there. Satellites, thank you, Michelle. Yep. So we call it the space segment. There are three segments. Space segment. It's this guy right here. Okay, how about this little unit over here? It's a GPS unit, but symbolic of users. So there's the user segment. And what on earth is this thing on the bottom? What is this depicting? What's important if you have satellites? It's computers, information systems, yeah. So satellites do not stay in orbit. Thank you, Donna, that's good. It's a control center. So just like mission control for Houston, satellites have a mission control as well. And that's a control segment because it takes a lot of people to keep those satellites up in the proper orbits and not hitting each other. So here we are, the space segment, our constellation of satellites, the control segment, which manages them. And of course, all of us are users. And there's communication between the control and the satellites, and of course, from the satellites back to us, the users. And the users can be a variety of different groups. So I will have to admit to you something, and that is, as we shifted into COVID, my team and me included started digging into our hard drives, looking for presentations that we've given that would be about an hour long and are largely direct instruction and not just hands-on. And what can we deliver, to our customers, to you? And GPS is one that I've been giving for, I think, more like 16 years. So some of the original content in my slide deck is all very valid, but was updated in like 2008 or something. And there's been this was actually the first GPS, and there's a second GPS, and then they just launched this year GPS 3. But generally speaking, they haven't changed very much. The satellites themselves they're probably made by more than just Rockwell International, but they are at mid-Earth orbit. They weigh about as much as a 2-ton pickup truck can hold. It's like a full-size pickup truck. They're pretty heavy. They're powered by solar panels, and they have an orbital period of 12 hours, and they orbit on a 55-degree orbital plane. So I have a question for you. If they have an orbital period of 12 hours, how often do they go around the Earth? This was the easy question. This was the low-hanging fruit. It's not complicated. It's so easy. You're probably thinking, yeah, twice a day. Thank you, Michelle. So yeah, so they orbit twice a day. Now, what is a 55-degree orbital plane? What does that look like? Does everyone know what we're measuring from? Like 55 degrees from where? Any guesses? And again, you're welcome to unmute and answer the questions, or I got the chat box open. How about mid-Earth orbit? How many of you, there's actually a hand raising button. How many of you are familiar with near Earth orbit? And how about geosynchronous orbit? How about, so if we have near Earth orbit, mid Earth orbit, and then we have geosynchronous. So you familiar with these three terms? So Charles guessed that we're measuring the orbital plane from the equator, and you're right. So we actually call it the equatorial plane. So let's jump to the next slide here. So if we were to project the equator out into space, that would create the equatorial plane. And we measure celestial objects from that equatorial plane. And that's where we get the inclination from. And so they're not polar orbiting satellites. So they're not just going around the poles, which we do have satellites that do that because they're specifically looking at changes in polar ice sheets, for example. They're not communication satellites, which are largely on the equatorial plane. So they are at this weird angle. And there's a reason for that. This is all done with a lot of mathematics, is because if they orbit twice a day at that plane and we have at least 24 satellites in the constellation, we get a pretty good coverage of the Earth. And look, if you look at this bottom picture here, you can see what would be called the ground trace. So ground trace, if we were to take the Earth and flatten it out like we did here, I'm not sure this is a Mercator projection or in any event, if the satellite were dropping breadcrumbs straight down to Earth, they would cover this area. And so the next satellite would be right behind it, and then right behind it. And so everything in the blue shaded area as it moves across planet Earth has good coverage. What areas on Earth do you see would not have good coverage? Yeah, Catherine's correct, the poles. Now, why on earth would they develop a system that doesn't have good coverage in the poles? Where do most people live? Where do we want the best reception on our GPS? Where would be most likely to use a GPS system? Not a whole lot of people living in the poles. But one thing that we can kind of say from this observation is that in order for Santa Claus to get back to his workshop, he probably doesn't use GPS on his sleigh because it's very inaccurate as you get further and further north or south. So I think it's important for us to recognize the three big kinds of orbits when we talk about satellites. And the moon, by the way, is a satellite as well. So near Earth orbit is literally 250 miles away. So the International Space Station is not very far away at all. Their orbital period, does anyone know what the orbital period of the International Space Station is? Anyone? That's correct, Stephen. 90 minutes. So they are whipping around Earth faster than any of the other satellites we're going to talk about. And then we have geosynchronous. So if you break that word down, geo means Earth, synchronous means in sync with. So a geosynchronous satellite might be one, for example, that's used for telecommunications. So how many of you have used a geosynchronous satellite, you think? So this is where everyone's hand should go up because you guys ever heard of Dish Network, like the Dish TV network? Any communication that's being broadcast overseas pretty much is going to bounce up off a geosynchronous satellite. So a geosynchronous satellite is going to be positioned above largely on the equatorial plane, but above the country that had launched it. So we have lots of geosynchronous satellites that we use for telecommunications, but they are locked in place. So as Earth rotates, they revolve around us at the same exact orbital period as our rotation. So what is the orbital period of a geosynchronous satellite? So the orbital period of the International Space Station is 90 minutes. Our mid-Earth orbit, which is our GPS, is 12 hours, and a geosynchronous is 24 hours. Yeah, so it stays locked in with us. So just to cover those. Oh, and by the way, the moon has an orbital period of 28 days. So the control segment, and this is fascinating to me, is that satellites, they don't stay in the exact orbit. They have fuel on board, and it takes a lot of effort and a lot of calculations to keep them in the precise orbits that we need them to be in. And to do that, someone's driving them, someone's in charge. Now, this is where a good point or a good time for us to bring up the question of who's in charge of the GPS network? Like, who's running that system? Any guesses? We have a headquarters in Colorado Springs, and we also have ground antennas. There's 8 ground antennas. Some of them are depicted here. Ascension, which is a little tiny island. Diego Garcia, and I can't pronounce that one. So Stephen's guessing NASA. Yeah, Cagney, the government's a very broad answer. So I guess if it's government or industry, it's government. But be more specific. NASA is a great guess, but it's not NASA. The NGA, National Governmental, I'm not sure what that even stands for. I do know what NASA stands for, the National Association of Silly Acronyms. Oh, no, that's not it. Our excellent, Stephen, the Air Force. So the military would be a great guess. Now I would have given you almost full credit for the military, but then specifically which branch runs it, and the answer is the Air Force. In fact, there was a bit of a tug and war about who was going to be the branch that maintained it, and the Air Force got that short stick. The military established GPS largely so we could control troop movements, have precision bombing, flights, can fly when there's not good conditions and stuff. So in fact, I experienced this recently. I'm going to jump into just a little short story here, which is I traveled down to Uruguay, and I was on Copa Airlines. Copa, I went cheap seats. I didn't go with the most expensive airline. And as we were landing, it was too foggy for us to land. And so we had to divert away and go to Paraguay. Well, it turns out some planes were landing. Planes from Norway and a few other countries, they had planes that were still landing in this very, very dense fog and in Montevideo. And I couldn't figure out why. And I was just reading articles last night in preparation for our talk today. And in addition to the satellites that are used for GPS, most GPS units can pick up an additional signal from specially located ground stations. And they make up something called the WAAS, the Wide Area Augmented System. And I know that it increases accuracy. I know that it exists, and I know that I can turn it on my GPS unit. But what I didn't realize is that some planes come equipped with WAAS, and they can land in dense fog, particularly when they're far north. In fact, one of the companies that was saying WAAS is so powerful to them is they serve customers in Alaska, where GPS and their navigation systems aren't going to be as accurate, so they use WAAS. So anyway, just a small Fig Newton. Here is the user segment. So boats used to all use a ground-based system called LORAN historically to navigate, which is similar but all ground-based. Now they all use GPS. It is on aircraft. Most people have it built in. This is a dated photo into their cars. And this is one of the first workshops that we were teaching on GPS at the Envirothon many years ago. So how does it work? In one word, can someone explain to me the two-dimensional definition of how a GPS figures out where you are? Like what is the mechanism there? Way to go, Stephen. I'll get it right. Is batting 100 now. Triangulation is the simplified version explaining how it works. So let's just say I'm lost. I'm assuming you're all seeing the chat box. So triangulation, and I want to know where I am. So I turn on my GPS, and it says that I am 100 miles from Cincinnati. So it tells me that's a distance, but that means I could be in almost Cleveland, I could be in Illinois, I could be in Kentucky, I could be anywhere on this circle 100 miles away from Cincinnati. So then it picks up a second signal, and it says I am 100 miles from Cleveland. Now, where those two circles overlap, I now have like taken 360 degrees and limited it down to 2 points, which is great. So I wait for a third signal to come in, and I got one from Chicago, and where those 3 circles overlap pinpoints me right there. So triangulation is a good 2-dimensional explanation of how it works. And that is, by the way, how the FBI can ping someone's cell phone and locate you. And in fact, our cell phones use what's called A for assisted GPS. And they are assisting your location information using cell tower data. But it's not a 2-dimensional flat world. We are communicating with a satellite. So when our GPS unit receives a signal and calculates that we are a certain distance away from a satellite, it turns out that we could be anywhere on the outside of a bubble, a sphere from that satellite. So it's not just a 360-degree circle. It's in every direction on the surface of a sphere. So can you already see how much larger in dimension this is in terms of where we could be located? When we talk to a second satellite, okay, the overlap of the 2 spheres is now a plane. It's a flat plane which crosses a great swath of Earth, because we actually have a third sphere already. But we can't pinpoint ourselves. We could be, anywhere across the whole North American continent right here, or theoretically anywhere here in space. So we talk to a third satellite, and it intersects that plane in 2 locations. And so the question is then, which location do we toss out? Now that may seem like an obvious and silly question, but don't forget, GPS is also used to locate space-based objects. So we would toss out the Earth one if we were on the space station, but in our case, we toss out the location in space, and it gives us a location. So it takes 3 satellites to give us latitude and longitude, but we are missing a critical additional measurement. So it takes a 4th satellite to calculate what? What are we missing? I know my latitude and longitude, but what am I missing? I have X and Y, but it would sure be nice to know altitude. Yeah, elevation. So I would call it a trick question to ask, how many satellites do you need to know your location? Because you could say 3 and you'll get you'll actually lock in and get a location lat and long, but you're not going to have any elevation data. Any elevation data you have is wildly off. So how does it figure out your location? It uses very complicated mathematics, and I'm not being sarcastic. It's super complicated mathematics. But if we were to break it down to math that we could apply and utilize in classrooms, it's a distance, rate, time formula. So you're on a train and you're going at 60 miles an hour for 1 hour. How far did you go? 60 miles. So rate times time is distance. So a satellite, a GPS satellite, is going to use a radio signal. And a question is, how fast does a radio signal move? So I'll give you some options here. A radio signal moves at the speed of light. A radio signal moves at the speed of sound, or I'm not sure. A radio signal moves somewhere in the middle. We're not clear. Where do you think a radio signal speed would fall? So I need you to vote. I need everyone to vote. So I have light, sound, not clear, in the middle, don't know. Maria, I thought you would know this one. Low end of the visible light spectrum. Okay, so we're talking, I'm glad that Charles brought out the electromagnetic spectrum, because we're gonna come right back to that in a second. So I'm just realizing, I think I had a hyperlink in here and I don't see it. Yeah, so sadly, there used to be a hyperlink that launched me to my EM spectrum. So just to cut to the chase here, the electromagnetic spectrum covers everything from light waves to radio waves, from gamma rays and X-rays, but not sound waves. So sound waves, you are experiencing sound waves right now. I'm putting air through my lungs, vibrating my vocal cords, vibrating air, vibrating a microphone, which converts to electrical. So, but there's air involved, and it's a relatively slow speed, and it wouldn't travel great distances. It's only traveling like, you know, maybe the end of my room right here. But any energy coming from the sun, and by the way, every star is emitting gamma rays, X-rays, light, visible light, radio waves, and more. And so if you think about the electromagnetic spectrum as a really wide range, with high energy particles up here, gamma rays, and very low energy, long wavelengths, so short wavelength, long wavelength, down here like radio waves, the visible spectrum is smaller than my nose. So we don't really see very much of this spectrum. And that's why we have radio astronomy. I mean, here in West Virginia, we have the Green Bank telescope, the largest steerable radio telescope in the world. And we are studying stars with that, and other celestial objects, because they are all emitting EM wavelengths, but they all travel at the same speed. They all travel 300,000 kilometers per second in a vacuum. So if I'm going to time how fast it takes a light wave to move from a satellite 20,000 kilometers down to me, I'm going to have a really good clock. And so the best clock is an atomic clock. So aboard every single GPS satellite is 1 or 2 atomic clocks. And so the basic concept here is that your satellite sends a signal. It's actually a pseudo-random code. But the signal essentially is saying, hey, it's this time right now. It is 3:01 and so many thousandths of a second. And when the signal is received, we can say, oh, it's 3:01 and more. So it's 3:02, let's just say. And so we can figure, well, it took a second to get from there to here. And if we know it took 1 second, we know the time. We already know the rate, speed of light, and we can calculate the distance. So using that simple concept, our receiver is able to then determine the duration the signal traveled to us. Using that information, it can calculate our distance to each satellite. So how do we use a GPS unit? So these are old screenshots from a Garmin, but any traditional handheld unit is going to have the same satellite screens and stuff that you would see here. So when you power on your GPS unit, it shows you a view where you can see directly overhead, 45 degrees to the horizon, and the horizon line right here. And what you're waiting for is for these GPS bars to lock in, and it shows you where the satellites are. And the GPS unit even knows where satellites should be using what's called an almanac. Sometimes if you turn on a GPS unit, you may wonder, why is it taking so long for this GPS signal to lock in? And that's because it hasn't, either you moved a great distance or the GPS hasn't been powered on for a while, but regardless, the almanac data is out of date. And it has to download a whole new set of information where to look for those satellites. So once it's locked in those signals, those black bars, then you'll start to get your location. And again, it takes 4 satellites to get that. When I teach this hands-on, we go outside and I say, tell me when your GPS says I'm ready to navigate, and count the black bars as it reaches that. So people say they have 1 bar, not ready, 2 bars, not ready, 3 bars, oh, I have a location, in 4 bars, 3 to 4 bars, it starts to say ready to navigate. And so you can flip through the different screens. You can see your latitude and longitude. And I prefer to use something called decimal degrees. And I prefer that because it's easier for math. Unless you really like base 60 mathematics, you may be asking, what is base 60 mathematics? So degrees, minutes, and seconds is the standard format, or historically standard format, for latitude and longitude. And there's 60 degrees in a minute, and 60 minutes in a degrees, minutes, seconds. So 60 seconds in a minute and 60 minutes in a degree. So just like a clock. So if you were to average, for example, several measurements, you have to do that whole thing where you're like, oh, I have over 60, so I now add another hour, or in this case, another minute. And it gets a little complicated. So if you use decimal degrees, it's an easier format to work with mathematically. So one of the questions is that how accurate is GPS? And a misconception students often have is that if I drop, I don't know, like a penny somewhere in the lawn, I can go right back to that penny again. But what they fail to recognize is the amount of error in GPS. And one of the sources of error is the fact that elevation is a model, because there is no single elevation. The Earth isn't a perfect sphere. And in fact, it's a spherical ellipsoid, we call it. So it's kind of, because of the rotation of the Earth, it sort of bulges in the middle. And even that being said, sea level is not even at the same level everywhere. And so we have the geoid is the actual surface of the Earth, and your GPS is going to calculate your elevation based off the ellipsoid, which is a theoretical model of this the elevation. And so the distance from that point is what causes some differences between maybe a benchmark and your GPS unit. So you can see this is an exaggerated version of the geoid, because it's not really that far off. But it can vary between 106 to 85 meters. So that's one of the sort of fig newtons of information that's kind of cool. Yeah, so this PowerPoint is illustrating that very thoroughly. So surveying measures the height above the geoid, and GPS measures our height above the ellipsoid. And of course, we have other issues in terms of the height of the ocean is not the same everywhere around the world as well. So there is a great video that explains how GPS works. But in my experience, when I click on a video and you guys watch a video that I'm playing and reprojecting to you, it doesn't work very well. I will give you the PowerPoint and you can just watch the video yourself. So let's change gears for a second. Who knows who Eratosthenes is? Anyone ever heard of Eratosthenes? And why is he important? What did he measure? So I can't remember the exact date, something BC. Eratosthenes determined the size of the Earth. Now, how on earth did he figure that out? He didn't have GPS. You know, he didn't have maps. He didn't have, I mean, how did he figure out the size of the Earth, the circumference of the Earth? You've probably heard this story. So Eratosthenes was visiting a friend in Sienne, and his friend said, check this out. On this day, which what I believe was the equinox, the sunlight shines straight down this well to the very, very bottom, straight down at this time. And Eratosthenes, as a mathematician, started, sketching out in his mind, wow, well, if that's going straight down to the center of the Earth, and I could go back to Alexandria, where I live, which is so many stadia away, and I could measure at the exact same time next year the angle of a parallel, and he made, this is the big leap he made, that sun rays are parallel. And he could use a shadow, essentially, a shadow stick. He could calculate the angle of the Earth. And he would know the distance in stadia between Sienne in Alexandria, and he would know the part of the pie that he had, how like the angle of the slice of the pie. So he knows the outside edge of the crust, and he knows the angle of the pie he has. So using that information, he can then calculate the circumference of the Earth. And you might be wondering, why are we talking about it was a GPS workshop. So there was a whole project about Eratosthenes, by the way. You can join in and do this from your classroom and compare shadows and determine the size of the Earth with different classrooms around the globe. But to answer your question, why are we talking about this? That was a prompt for us to go outside with our GPS units right now. And when we do that, we do an activity that I love. I bring together science and mathematics, history, and we use a GPS to measure the polar circumference of the Earth. And to do that, we go ahead and let me see here if I can, I'm going to annotate, draw. Okay, so what I'd love to have would be a whiteboard. I'll just draw on this. So we go ahead and we go outside, we mark a location right here with a GPS. So we know the latitude and longitude, okay? Our latitude is going to be, for example, this latitude is degrees above or below the equator. It'll be 39.12345. And every single digit is critical. We need them all, okay? And then we might have a longitude that is negative 40 degrees. So 40 degrees east, I'm sorry, 40 degrees west of the prime meridian. Where's the prime meridian? Where's the zero longitude? Anyone know latitude versus longitude? And if you don't, you should read the book of longitude. Yeah, so Greenwich, England is where the zero of our latitude is. That's where the prime meridian is, Greenwich, England. I often just say England. So 40.12345. So that's our initial location. Everyone with me so far? Okay. Then what we do is we walk due north or due south with our GPS. So you can use a compass to help you out, or you can use that position screen on your GPS and watch. What we're looking for here is our latitude to change, but our longitude not to change. And so, you know, if I'm in this spot right, if I'm in this spot right here, okay, I want to try and walk north or south. So I'm not going to walk that far, obviously. But what I'm doing is hopefully changing position enough that the GPS sees it. So if you walk half a football field, you're going to have great results. If you walk a full football field, you have even better results. But in the end, as you might have to walk around for a while, what we're ideally looking for is for you to have a new 39.12355 and negative 40.12345. So ideally, we are on the same line of longitude, but we've walked north or south latitudes. So the idea is to walk along a line. So the drawing tools is not happy. So, and we can use the GPS, said go to the previous waypoint. It'll give us that distance. So let's just say that distance was 50 meters, which is 150 feet, right? Roughly. So if I know this information right here, I can now calculate the size of the Earth, the polar circumference of the Earth. Does anybody see it? Do you already see the math? Who's with me? Who's got this figured out already? So let's do it. So what I needed to calculate here is the difference in latitude. So And this is where I can tell if the assignment was done correctly or not when I'm working with students. If they say, oh, I went 1 degree, I'm like, no, you didn't. You'd be in a different state, you know, or definitely in a completely different, you know, part of West Virginia. You know, you didn't go a degree. In this case, walking across the football field, our difference is going to be, I'm going to subtract these right here, 0.0001, right? 0. So 0.30 zeros, and that's the number of degrees. That's the little degree symbol that I went. And I know that that equates to 50 meters of physical distance. Now, the question is, that's 0.0001 degrees out of how many? How many degrees are there in a circle? 360. Ashley's with me. Way to go, Ashley. Oh, Stefan's got it too, okay? So I didn't leave myself a lot of space up here to do this, okay? And it's getting a little messy. But I have 0.0001 equals 50 meters. And that's over 360 degrees. I don't have a degree symbol on here. Over, and at this point, it's a question mark. So this is the equation that we set up. And I want to ask if this equation looks familiar to anyone. Have you ever seen an equation like this? So 50 meters over question mark equals so many degrees, my little degree symbol right there. So it turns out kids learn fractions in very early grades. Even as early as 2nd grade, we start working at fractions. You know, we might get, you know, 1 over 2 is equal to 2 over, I don't know. In this case, you can fill it in pretty easy, you know, the old 4. But when you get to 6th grade, students learn this complex thing called cross multiplication. And so what we can do here is we can set this up and solve for the question mark here. So we could say 0.001, the red shows up better here. I might have to clear some of this. Is there an eraser tool? Point 0.001 degrees times the question mark is going to equal 360 degrees times 50 meters. Now, in order to isolate the question mark over here, the variable, we're going to divide this side by 0.0001. And for those of you who are into units, you can see that my degrees are going to cross out. So this is crossed out. And I'm going to end up with a result in meters. So let's go ahead and do this because it's kind of fun. I'm going to pull up my calculator. So this is the activity that I do during my face-to-face workshop. Okay. Let's go ahead and share the calculator. So I'm going to say 360 times 50 meters I just walked equals divided by 0.0001 degrees. Oh my gosh, is that number absurd? What is that number? So I appreciate that Chris already did some math here, because That is meters. Okay, that's 18 million meters, I think. But we can simplify that to 180,000 kilometers. Now let's just, I like doing this sometimes. I've never actually done this live before like this. But let me go ahead and Google polar circumference, Earth, kilometers. And actually the answer is 40,075, but it was, when originally calculated, it was 40,000, because it was, in fact, it was an exact number. The definition of a meter originally was the distance from Paris, I believe, to the North Pole. It was a fraction of that distance. So the meter itself was defined in part through a measurement of the polar circumference of the Earth. So that was the math behind it, and it is shockingly cool to go out and to do that with students using a GPS unit. So in case you're wondering, what was the whole point behind the Eratosthenes project discussion, is that this cues us up for, Eratosthenes used shadows and a well, and we can use our GPS unit to calculate the polar circumference. And typically I get error rates that are less than 1% error. Sometimes as high as 10% error, but I often get, 1% or 2% or even less than 1% error when I do this with students. Any questions about A, how the basic GPS works, B, how we can use a GPS to teach mathematics and science through this activity? And I have a handout, which I will, at the conclusion of the workshop, I will send to you the handout that I use when I do GPS with students. Any questions? Okay, so what's geocaching? Who here has been geocaching before? Anyone? When I started geocaching, I had a flip phone. I had a Sprint flip phone. And let me tell you, it didn't have any cool features. There was it didn't have a camera. It didn't have GPS, and it had nothing. That was what we think about today in our smartphones. So Michelle's been geocaching. Anyone else? Okay, so a few of you have. So geo meaning Earth, and caching means hiding. And I actually was on the geocaching website last night thinking about this workshop, wondering, did they post anything about COVID? Are they saying like, don't go out and touch things? But the virus only lasts for like what, an hour or so in the sunlight. So I think it's pretty safe to go geocaching. Getting outside in itself is safe. Going grocery shopping, not safe. But in any event, the idea of geocaching, if you're not familiar, it's a hide and seek game where you are going to go out and try and find this hidden film canister. They used to use ammo cans a lot, but it's been discouraged because, I don't know. I personally don't really see the objection, but something waterproof. But basically it's hidden somewhere, and all you're given is latitude and longitude, and you have to try and find it by following your GPS. And it's a fun game, and they often have clues that lead you to where you're going to go. So there's a website, geocaching.com, and they publish users' hidden caches. And you don't just hit a button and publish automatically. There's a vetting process. If you're a brand new geocacher and you say, my first day I'm going to go out and post a geocache, they're not gonna list it. They'll wait till you become a known user or someone else has gone out and physically validated that your geocache is there and it's safe and cool. So when you're going geocaching, one of the things that I like to do is look for ones. I usually start with some that are easy. So I sometimes find the easy ones pretty hard, and they have easy, intermediate, and difficult ones. And they even have some that are multiple geocaches. Like you have to go to one in order to find the next one. There's a clue, and it's a big puzzle. And it's a lot of fun, but always read the comments and look at the last time it was found. Sadly, sometimes a geocache might go away. I mean, it could be an animal took it or something. You never put food in a geocache, for example, for that reason. But maybe it got lost, washed away, or someone took it. And so it's always good to check in advance what the comments say. So once you enter your latitude and longitude, then you use the go-to feature of your GPS and follow that arrow until you get closer and closer. So what you always will find, ideally, is the geocaching symbol. So there's an official symbol that we use. You get stickers and stuff. And inside there's usually a logbook. So you can say, hey, people also have like geocaching names. So instead of your real name, you might put your handle, essentially, your username for the geocaching website. And sometimes there's a disposable camera. Take a little picture of yourself. And travel bugs are the coins that people take from one geocache and drop off, and you log where it was. So geocoins and geotokens or travel bugs all have the feature that you can go to a different website and say the serial number on this geocoin is this, and I picked it up in West Virginia, and the owner said, I'm trying to get this geocoin to Patagonia. And you're like, well, I'm going to Florida, on a vacation, so I'm going to take my geocoin with me and go geocaching and drop it off at another geocache. And it's amazing to watch these things go around. This could be a fascinating school project, by the way. You could get your own geocoin and ask your students, say, where do you want to visit? Let's go to Japan. Let's go to Fukushima or somewhere and see if you can get your geocoin to get there. So you sign the logbook. If you take a trinket, leave a trinket. And remember, hide it back the way you found it and never leave any food in there. One thing that I like to talk about, I'm an Eagle Scout, and when I learned orienteering and stuff, I always had a sort of a mind towards conservation. And so if you see garbage, whenever I'm hiking or wherever, backpacking or geocaching, I like to take trash with me. So you can go to geocaching.com and get all the information. And I encourage you to try it out. You can now do it with your phone. So where I used to have a GPS unit was the only real way to do this. Now most of our phones have no problem. They have GPS chips built right into them. And so environmental geocaching actually was kind of a phrase I came up with. But the idea was we created a whole series of geocaches in West Virginia, and our geocache was a thermometer or dissolved oxygen meter or something like that. And so we encourage people to go out and take a reading of the environment when they went geocaching. So I don't think I still have those set up anymore, but that's what we're doing. So any questions on what geocaching is? So let me, I have the geocaching website right here. Let me go ahead and pull that up for you. So here's the website, and if you log in, I guess I forgot my password. You can essentially find all kinds of geocaches in your area. You need to log in and have an account to do it. But this is the website right here where you do it. There's 750 caches right around Morgantown, so there's plenty to do. One thing that's really fun is if you go to visit a new city, often on a work trip, I like to try to find at least one geocache when I'm on a trip. And the question Maria asked, can you put a geocache in a park like Morris Park? So it's an excellent question. If you're going to hide a geocache on private property, you usually ask someone. Public parks, usually it's fine to do that. Don't put them around any federal buildings. They frown upon that, and there's a lot of heightened security concerns, so I wouldn't do that. National parks have their own regulations. State parks have their own regulations, which are, they don't want you to create trails going. So it can go, you can put a geocache in, but it has to be moved every year or so. But something like a city park, depending on where you hide it, I don't think it's going to need any special permissions, but you could always ask. And I believe there are geocaches already in Morris Park. Okay, so the last part of the workshop was, I've been collecting data using my GPS unit. And so, for example, maybe I was collecting data on what kind of science project might you guys be doing? Invasive plant species, dissolved oxygen readings, temperature readings. What other data might you be collecting that can be geotagged or georeferenced? Think science classes or science studies that you might do as students. So maybe doing macros. Yep. So some water quality studies. That'd be a good example. So if I was doing that, what I could do is create a simple spreadsheet. And that simple spreadsheet would have some basic column headings. So you have to have an ID. If you don't have an ID, it's not going to work. Okay. And then you could have latitude, longitude, elevation, and maybe we're going to have, in this case, we have temperature, whatever data you want to have, anything you want. So you put your column headings. So as long as you have the critical headings here, ID, latitude, longitude, and elevation, okay, and you're going to go ahead and just number these. And you set this up with students and have them record their data. And then what you're going to do is record your latitude and longitude of each of these points. So I might say 39.12345, and longitude was negative 40.12345. My elevation was 5,000, and my elevation is going to be in feet. The temperature I measured here was, I guess we could use Fahrenheit, even though science class would use metric system. Because today it's like, what was like 85 degrees today? And I could maybe say, what was the surface I was on? I'm on asphalt. And then you do that for each of the readings. Okay, so 39.12348. So that one's different. And maybe I'll just make all these the same. And I'll make a pattern here because I'm lazy. And we're going to drop down a hill here. We'll go 4,500. It's going to be a very steep hill. And the temperature is going to do what? It's going to change as we go down the hill. So it's going to get hotter in this case. So here we've collected a bunch of data. And we can come back to this in a second. I'm going to go ahead and take this data, and I'm going to save it as not an Excel workbook. I'm going to save it as a comma separated value, a CSV. Have you guys ever done this before? Saving something as something besides just a, it's not happy with me. I need to save it first as something, and then it'll let me do it. Oh, I'm sorry, I didn't add a place. Okay, I've hung up for some reason. We'll come back to that in a minute. I'm not sure why it's hanging up for me. Let me go now to a website that's going to allow us to bring our data that we've collected and have students create a product to display their data. So we're gonna go back to the browser. And here is ARCGis. So did you guys create a free account like I asked? I suggested in the email to you? Crystal took a GIS class, so you might have already done stuff like this before. Great, Ashley did. Michelle asked a question I just saw. What app takes the place of a traditional handheld GPS like a Garmin? And that's an excellent question. I don't have a good answer for you, Michelle. I've used a couple of different apps, but I currently don't have one loaded. My GPS, my phone has a compass. I have an iPhone, and there's a compass app built in, and it displays latitude and longitude. So I can use it to see that data. It doesn't have all the features of a GPS. Okay, so if you created a free account, so let me see if I can't. I'm going to go back to the home page here. Okay, at the home page, once you create your free account, you can look at existing maps, which is really fun. Here is a heat map, it's called, of coronavirus. Vector maps, street maps, community maps, but I like to go right here, make a map. When you make a map, you have to choose your base map first. Or you might want to, maybe I'll zoom in on a place. I'm going to zoom in on West Virginia. There's West Virginia. And now I choose the base map that I want. So right now we're using what looks like a topography map of some sort, a shaded relief map. And so I might want to have, for example, imagery, satellite imagery. Depends on what your students are studying. If you're studying different temperatures as a function of land cover, this might be a good map for you to use. Maybe I want a hybrid map so I can see the outlines of my state and the major highways. So it gives us some more context. So I got my area, one. What do I want to show? Choose a base map, and then I can add layers. So GIS as a concept is built on a series of layers. So I like to use Photoshop to make pictures, and when I do that, I'm operating on layers. Sometimes I'll add a new image under my picture, and I'm like, where'd it go? I can't see my image, and I realize, oh, it's too far down on my layers tree. So I pull that image up, and now I can see it on top. GIS works the same way. So you want to make sure that certain layers might have different displays and they overlap other layers. So it's important what they're, how they're positioned. So one neat thing about ArcGIS is it has tons of pre-saved layers. So I could add in here, layers like maybe land cover layers or maybe water data. I want to add maybe rivers are important to me, and I could search for watersheds. Okay, and it didn't come up with a watershed map. Oh, I was searching my content. Sorry. Add. Okay, there we go. So I was looking at my existing layers here, and I have no layers in here. So here's population. So I want to see how population affects it. Here's census data, updated 1/6/20. Population growth rate. So daytime population in 2016. You can see all this, and you can read about these different layers and see if that's the data you wanted. So USA census populated places. So I'm going to go ahead and add this layer to my map. So I'm going to overlay an existing layer using data from that was produced by someone else. So I can see population centers right here. Now what I want to do, and I think I ran into an issue with my my Excel had a dialog box somewhere that I didn't see. So I'm somehow hung up. with my Excel, and I just don't know why. Definitely giving a little error. Can't even, there's definitely a window that's popped open on me, which is unfortunate. I just can't see the window. I don't know where it went. Oh, I see. It looks like it's Microsoft. Okay, I got rid of the window. Got it. So I'm gonna go back to my Excel, and hopefully this is gonna work fine this time. Okay, so this is that data we had before. So we're gonna say save, and on my Mac, so I'm gonna call this temperature data. I'll save it on my desktop for now. I'll save it as Excel, but what I really wanna do is I wanna save it as a comma separated values, CSV. So the options under save as, I'm not sure if you can see this window popping up, but I have Excel workbooks, PDFs, and comma separated values. All right, if you're wondering why we're doing this, we'll come back to that right now. So I was trying to Betty Crocker that and show it to you how it worked seamlessly, but okay, share. So here we are back in our map, talking about temperatures and population. That's so a theory that my student had is the temperatures increase with population density or something. Okay, urban heat island effect maybe. So what we want to do is we want to add a layer from a file. It says you can upload shape files, CSV files or text files, GPX files, which you can export data from your GPS unit. My running watch exports GPX files as well. So choose file. And on our desktop, hopefully I'm gonna have my temperature data. There's the Excel spreadsheet, right? Is that the CSV file? That's the Excel. We want the CSV version, that same one. Well, there's the Excel file. What I really wanted was the text file. I'm not sure it's gonna let me do it. Yeah, no. Oh, I'm sorry. I apparently dropped it in my documents folder. That was my bad. So that's where it went. Okay, so one of these two files is a comma separated value right there. So there's temperature data, CSV file. Choose that, import layer. And so if you recall, we basically left the longitude the same. We changed the latitude a few times. And it automatically took the locations, georeferenced them, and then it did an option of the data And in this case, they're saying elevation, and this can be like different shapes. So if the data was represented on my map, let's just say it was numbers of robotics teams, and there was in each town, and there's 5 teams in one town and 50 teams in another town, it would have larger circles for the different numbers of students or teams. So in this case, we're going to do temperature though, and I'm just going to say, let's see, different colors, and then say done. So now where is this? Let's see. Let's look at our layers. So we have populated data and we have temperature data. And here it shows all data was imported. So each of my points right there, latitude, longitude, and elevation. Let's turn off census data. And you can see that it color coded each of the points as well. And we're able to move layers up or down, want to lay one layer on top of the other. So let's zoom out here. And I can choose to zoom in to just this layer. We'll make our layer transparent. I think it was blocking the rest of my screen. And then we can zoom to this layer. Oh, I know the problem. It thinks I'm in the middle of the ocean. That's why I'm getting all this black. I apparently made an error in my, it thinks I'm over here. So 39 degrees north latitude, -40 longitude. It appears that it positioned me in the middle of the ocean, which I'm not sure why I did that. Anyway, so that was anticlimactic, but this is how you can add your student data onto a map, have the students create their own product. What's neat is every one of those dots that's on there, you can click on and see the content behind it. So if you had any kind of information like the macroinvertebrates discovered there, the temperature of that area, someone else said gems and minerals, you could have anything that you would like to document, and it's geo-referenced there. So I'm still a little confused because if I look for the West Virginia latitude and longitude, let's see. Oh, 79 degrees. Oh, I was definitely off. Yeah. So it should be -80 degrees would put me in West Virginia. So it was an ID10T error. You guys are familiar with that? An ID10T? Spell it out, you'll get it. So because I hate to fail, I'm gonna make all of these -80. I'm gonna save my file again as a CSV, and I'll import this new layer. Okay, so I just hit the save button again as a CSV after fixing that. If we go back to my map, we add a layer from file, choose file, and in this case, this is temperature data fixed. We import that layer. Okay, and we're gonna show temperature in colors. Done. So there's my temperature data, okay? It has a legend that explains what it is. We can see each of the information about that. And if I zoom out a little bit, now you'll see. And that's what was supposed to happen. Apparently I was in Barber County. So if I had just put -80 instead of -40, I wouldn't have been in the middle of the ocean. But if I can turn off this layer and I can even delete that layer, get rid of it. But students can then create a map with any data they want, customized with whatever back layer they want. If we're on street map, and then I can zoom to this layer. Here's my data points that I measured. And it's located right there. So that was kind of the punchline of the connection between GPS readings you can take, how to use a simple spreadsheet, and how to input those values into a GIS. So Maria asked a good question. Why didn't I put north, south, east, or west? And the answer is because the equator defines a 0 latitude. And numbers higher than 0 are north. Numbers lower than 0 are south. Same thing with the prime meridian. Numbers positive are to the east of the prime meridian. Numbers negative are to the west of the prime meridian. So on my spreadsheet, and again, your GPS unit, if you set it up for decimal degrees, it will tell you positive 39 degrees north latitude, negative 80 degrees west longitude. Hopefully, you're walking away from today's session with an understanding of how a GPS works. So key things to remember, it uses a more complex version of triangulation called trilateration, where it determines the distance from satellites using what speed? The speed of light. And knowing that and the time it took, it can calculate your distance. From 3 or 4 satellites, you can lock in your location. Then you can use a GPS to calculate, for example, the polar circumference of the Earth. You can do that just by taking 2 different readings, making what's called a waypoint. As long as those waypoints were in a straight line north or south, you can use the go-to feature to get your distance back, use the distance between the 2 waypoints, use a difference in the latitude, and you can use simple mathematics to calculate the polar circumference of the Earth, which is a really fun activity. Geocaching is A, a sport, and B, can also be educational. There are geocaches that are historical references, ones that are scientific, but the good news is it's getting students outside. I would consider it a physical activity. And so kind of like a phys ed type of program, but it's really fun and it's using science. And then of course, the last part was, how can you use a GPS unit and a mapping tool? A mapping tool is a geographic information system, or a GIS. How can you use those together? And I've really loved this, ARCGis.com. It is a free tool. There's more powerful tools available for free in West Virginia. You can actually get ARCGis, the full-blown desktop. You can get a free copy of the DVD and install it and use it, which is pretty neat. And it's simple. What I'm hoping that you realize is, as long as you don't have an ID10T or an idiot error, having students record their data, whether it be poli-sci, whether it be historical, whether it be scientific data, it's easy to build your own maps using a GIS like this. And this can be shared in a variety of ways and submitted as a final product. So that's how you can georeference student data. So do you have any questions? So this has been, almost an hour and a half, which is what I predicted, to cover those 3 topics. But what questions do you have for me about GPS, GIS, geocaching, etc.? Any questions at all? Okay, well, I have a favor I'm going to ask of you, and that is I'd like you to take our survey, basically our evaluation, and when you do that, it will automatically give you a certificate. Let me just give you the link for it. I'll put it in the chat box. You can click on it. I will also be emailing each of you a copy of the presentation we used today, as well as a variety of handouts, including the activity where you calculate the polar circumference of the Earth. It's really fun. So here's the survey link coming up. And really no questions? I'm not sure if I succeeded or failed if you have no questions. But I'm gonna go ahead and end the recording part now. So there's the link. Hopefully you can click on that.